Good day, everyone. On today's Wolfram live stream seminar, we have Furkan talking about a suggestive quantum theory for cyclic strings. Welcome, Furkan.
Thank you. Actually, this is basically my work for the Wolfram Winter School 2025. I studied a multi-way system of character strings, cyclic character strings. Let's have a look at the outline of the talk. First, we are going to talk about some basics of Leibnizian philosophy, uh, where monads are the primary examples. Then we will have a look at the monadic interpretation of cyclic strings. Then we will define what is called a BSD variety. It measures the degree of variety in cyclic strings. Uh, Then we will provide a few motivations for using the multi-way system of the Wolfram model. In the multi-way system, we will have a look at what is called the physical paths. Then we will define an action, which we call BSD action on physical paths. Then maximal variety paths will be the ones that have maximum action value. Then using the ideas from the cellular automata interpretation of quantum mechanics, we will try to give what elements of what is called the ontological basis in this interpretation. And because what we have at hand are only character strings, which are abstract entities, using the word-to-vec algorithm, we will assign each string a vector. Then we will think these vectors as if in a Hilbert space of some dimension. Because we define an action on paths, we can do path sums similar to path integrals, and we will calculate what is called the S matrix for the system. Then we will conclude the talk. So this is basically the outline of today's talk. We need to load a few software. You can reach this package on my GitHub repository. And this is the Wolfram multi-computation package, which we use to calculate the multi-way system of the cyclic string substitution system. Okay. Of the ideas in Leibnizian philosophy, we will basically be interested in what is called monads. Monads are kind of metaphysical atoms. Each of them should be unique. The identity of indiscernibles, as expressed by Leibniz, means that if two things are equal in all of their properties, then they are basically the same thing. So when we define monads in the Leibnizian terms, each monad should be unique. Let's have a look at some visual example for some string addition problem. But before that, we need to define what cyclic strings are. They are basically just normal character string we encounter in computer science, but with a cyclic boundary condition, meaning that the character after the last character is the first one, or the previous character of the first element is the last element. So this is the basic cyclic boundary condition.
Sorry, can you just repeat that one more time? I didn't quite get that definition.
Okay. Actually, let me give an example here. For example, for the word string, if we interpret this as a cyclic string, no, I think this is not a, let's say boundary, the word boundary. When we impose cyclic boundary condition, the letter after the last character is the first one, B, or the letter that comes before the first character is the last character. So they are kind
Okay.
of
Got it.
represented in a cyclic way.
A string in a circle, basically.
Exactly. Here, in each axis, we have 32 letters consisting of just 2 letters of length 5. None of these are Leibnizian. However, if we consider the addition of strings, then we obtain a fractal-like pattern. But before that, I need to define what Leibnizian strings are. In a Leibnizian string, 2 different character positions can be differentiated according to their local neighborhood structure. But if there are at least one pair of characters that share the same local neighborhood structure, then they are not Leibnizian, and we call them non-Leibnizian. We will use the terms Leibnizian and physical interchangeably. So this kind of a visual example of the kind of intricate patterns occurring in the system. When, for example, you generalize this to words of 6 characters, one again obtains a similar pattern, which looks like a kind of fractal.
So what is this diagram depicting here?
Okay, for example, let's give an example. If we add I think you can see my cursor, right?
Yes, we can see your cursor.
For example, okay. If we add this string with this one, by string addition, I mean kind of joining strings one after another. There is a black dot if the resulting string is physical, I mean Leibnizian, and there is no dot, no point if it is non-Leibnizian. So this is
Can you just like, would you be able to like, can you drag that larger, that image? Is there a way to like click and expand it a little bit? Yeah, that would be great. That's it. Nice. Okay, so it's
even
right. Okay.
I think even this simple or fractal looking behavior is worth studying, I guess, in the more general mathematical way, perhaps. When, for example, we may regard a word as a number in base 2 if it consists of 2 letters, or in base 3 if there is an additional letter like C or D in for basis 4. Here I will only just give the basic ideas of BSD variety. For more, you can see my Wolfram community post related to this project. There I include more details. This function is a measure of variety in strings. For example, if let's consider this string, which consists of only A's. For that string, the variety value is 0. I think we can do some calculations. Let's say in our algorithm, we label non-Leibnizian strings with 0 variety value. However, for example, let's consider this one, AA, BA, BB. This is Leibnizian strings. It has a positive variety value. So in a way, if a string has character which can be easily distinguished by their local neighborhood structures, then such a string has higher value for variety. If it is closer to maybe some uniform structure, it has a lower value of variety. But in order to make sense of the definitions, one needs to look at the kind of algorithm to define the variety value. But as an extra, let me say that it depends on two concepts, which the first one is relative indifference value. It is defined for two characters, and it is the lowest value of radius around these characters such that they are not isomorphic to each other. Then we have to define what's called absolute indifference. It is defined for a single character, and for the single character you look at the relative indifference values which with other characters, and it is the maximum of these numbers. Then what is called the BST variety is the sum of 1 over absolute indifference value. So this is the technical side of the issue. As I already mentioned, in our algorithm, non-Leibnizian strings have zero variety. Yes, I also mentioned that one, that I use the terms Leibnizian and physical interchangeably. So, when I was considering the Leibnizian nature of character strings in Wolfram model, actually I was using the hypergraph ontology. When I evolved the system in time by applying rewrite rules at each step, sometimes you encounter non-Leibnizian strings in the evolution. So there is the question of how to kind of let's say continuously define a time evolution which is physical at each step. Then the concept of multi-way systems are very useful in this regard. I will talk about what multi-way systems are for the ones that may not be familiar with the Wolfram model, but the basic idea is similar to analytic continuation in complex analysis. For example, when you consider the function, let's say 1 over x on the real line, it is analytic except the origin. But if you use the complex numbers, there is a way to, let's say, extend its domain using the ideas from analytic continuation. So we go around the origin and connect it to parts of the real axis. Okay. This is the first step of the multi-way system that I will consider in this talk. We have a head node, then a rewrite rule. If a rewrite rule matches, for example, it causes a branching in the time evolution. Here, the one on the left-hand side is the result of applying one single rewrite rule matched at some point. And this is also valid for the second, third, and fourth ones. Then we consider a bigger multi-way system, which has depth 6. I didn't include the vertex labels because otherwise it's almost impossible to distinguish each point in the multi-way system. So when I kind of zoom in, there's a very interesting structure. Actually, it is basically a tree, what's called a tree in computer science. Then this is the function to assign variety values for each node, which is a string in the multi-way system. For example, the first two values of assigned variety are as follows. The first one is variety 12, the second one 12, and this is non-Leibnizian, this last one in the first three elements. Then what I call a physical multi-way system is a kind of subset of multi-way system where each node is Leibnizian, and it is highlighted as red in this graph. This part is physical according to the definitions that I use in the talk. And this the left-hand side is non-physical. Okay. So in order to kind of define the path sum, which is similar to path integrals, we need to have a list of target strings, which I select as the list of strings at some depth, and this is given by the branchial graph, what's called as the branchial graph. If, somewhat more information about this branchial graph is that two vertices are connected if they share a common ancestor string. Then these are the elements in this branchial graph. So we are okay with the multi system. Then, okay, we will consider paths emanating from the, I think this is the head node, this node to the elements of the branchial graph, which are strings in the multi-way system at some depth.
This is depth 6 from that multi-way system?
Exactly, yes, depth 6.
And what is the starting string for the multi-way system? Is it shown there?
Yeah, sure. I think it is this one.
Okay.
DDD, CCC, BBB, AAA.
And
I actually the reason, sorry.
yeah, and it's cyclic. It's meant to be considered as a cyclic string.
Exactly.
Mm-hmm.
Yes. Actually, I considered a four-letter string because when you consider two-letter strings, it turns out that most of the strings in the evolution turn out to be non-Leibnizian. So this has a richer structure when we use four letters instead of two, let's say. Okay, then let's talk a bit about the physical paths. We start with the head node, which is this string, and we have the target nodes, which are elements of the branchial graph evaluated at some depth value. Then we consider all of the paths that connects the target and the head and the target strings. If actually the path is a consecutive list of strings, and in a path, if there is at least one non-Leibnizian strings, we say that it's non-physical, and we say a path is physical if all the strings in the path are physical. So this is basically the definition of physical paths. Let me see if there's any point I would like to add. No, I think I gave the basic idea. So from all of the paths, I create what's called kind of physical path graph, and in a different plot style, similar to the multi system plot. This is the physical paths. The graph that correspond to the union of all physical paths. And you highlight the physical path, we have a similar plot for the kids, the physical hypergraph, as we talked about.
So this is a
Okay,
subgraph
we
extracted out of the
divided physical
multi-way
paths
system that
on such.
consists of the Leibniz strings.
Exactly, yes.
Can you perhaps make like a simple example and explain what really this definition of the physical string is, and what's the intuition behind why you call it physical when it's Leibnizian?
Okay, let's move on to the earlier parts of the talk. By physical, we mean Leibnizian, and
Yeah, by why? But why?
okay, it's because of the fact that in a Leibnizian strings or in a physical strings, as we call it, each of the characters have unique neighborhood structure. So if we interpret these characters as monads, that means they are unique, and no two character in the strings share the same connection structure, and that means they are not indiscernible, so they can be distinguished. So this is the basic idea.
So how do you compute the neighborhood? Do you like just scan the string? This is like one character radius neighborhood for every character. That's what you're computing.
Yeah, actually, yes. For example, for this, let's consider this one. There are two concepts. The first of them is what's called relative indifference. So it's defined for two characters, and it is the minimum value of neighborhood radius for which the neighborhoods become non-isomorphic. So if it becomes isomorphic at each step, even if we exhaust the whole string, that means they share the same neighborhood structure. So they are basically the same, and so they cannot describe monads in this sense.
Is it any two strings? Sorry, two characters.
For
Is it
relative
four?
indifference, yes, yeah, any two characters.
I think we need one or two examples. This is like the basics, and I know it's kind of like implicit in what you're discussing, but maybe if we can take just 5 minutes to really understand this, because I'm also just struggling to to really comprehend this important first detail. So can we perhaps use an example? Also, I'm confused if we just use like one of the examples on your grid there. Right at the bottom is A on the y-axis, and then on the x-axis, there's the first option right at the bottom is the first black dot is ABB.
This one, okay.
We can use that one as well. So I don't see how
We just
any
pick the single row and different columns, so that we can distinguish them. What actually makes them
exactly
right
Okay.
physical?
Actually, this is this black dot corresponds to the fact that if the sum of two substrings is
Yeah. So
it
let's
becomes
pick
one,
like the same row, so that we can join this 5 A's with two different
Okay.
strings.
I think we can do the calculations. But if you need an explicit calculation, I would suggest this simple string, but we can also do the other one. First row, this one, you mean AAA. 1, 2, 3, 4, 5.
Actually, what would be the simplest? Is there like a string with variety 1? So that you can just point to the actual neighborhood.
For variety 1. Okay, so it is sum over absolute indifference. I'm not sure actually. Yeah, but if you like, we can continue with this one. It looks simple. For example, let's pick this letter B for relative indifference calculation. If we consider any of the A values, so even in the zero neighborhood, they are different. So in order to calculate kind of non-trivial part of the relative indifference, we need to compare B with another letter, which is B. Then we may consider this one. In
I
the
get
first
it.
neighborhood, this is ABA, and this has ABB. So they are non-isomorphic, which means the relative indifference is 1 for the two characters. If we consider this B and the last B as it's represented on the screen, then this is ABA and BBA. So they are also non-isomorphic at radius 1. That means the absolute indifference of B, which is the maximum of the list of relative indifference values, is 1. Yes.
I get it. Okay, so for every character in the string, you
Mhm.
say take each character, and then every time that character appears in the string, look at its neighbors, and
Mhm.
if every instance of that character appearing, there is an identity to its neighbors, then that creates maximum variety. Like if it's unique. So the first time A appears, if it's surrounded by two A's, the
Mhm.
second time it appears, there's an A and a B. The third time it appears, there's two B's. Then that means every time you saw an A in the string, it had different neighbors each time.
If it's a Leibnizian, yes, exactly.
Yes, yeah, I see. So that makes sense. So what I was getting confused by on your grid over there is if there's 5 A's in a row, every single A there is kind of like has the same neighbors.
Exactly, yes. They are
Okay.
indistinguishable, basically.
So then that dot showing that it's physical, does that just mean it's above a certain threshold of physicality? Or
Dot is for the concatenation of
Yes,
Uh,
concatenation.
row and column strings,
Right.
and so it's checking the variety or the physicalness of
between the combined string, right?
right,
But
right. So
in
the
the
string of
Yes.
length
in
10.
yeah, so
I
that's my
guess
question. So yeah,
ABB.
So like, what's the variety of
This dot. I think yes. ABB, yes.
yeah. So is that just above a certain threshold? Because for every time A appears, at least the first 5 times that A appears, its neighbors are the same. It's going to be 2 A's.
Well, the first instance of A has on the left side
A B.
a
Yes.
yeah.
Sorry, the second, third, fourth, fifth, and sixth. 1, 2, 3, 4. Sorry, yeah, the first instances 2 until 5 of A all have their neighbors the same. It's A's as the
You
neighbors,
mean
right?
this first
Yes,
part?
exactly. Yes.
Their neighborhood should be different. Otherwise, the variety would be 0.
That's why I'm getting confused. So if you say the second A in the string, so A number 2 over there. So if you were to just highlight that, you can see its neighbors are an A on the left and an A on the right.
Okay.
And then the third instance of A in the string
They are the same, yes.
is the same.
We move on to larger neighborhoods if they are the same.
Oh, is that part of the rule? I missed that part of the rule. Sorry. Okay, so if it's the same, you
Move on to
extend the
larger
radius
neighborhoods, yes.
What do you
until
mean by
there's a
larger
difference.
neighborhoods? Is that forward or
Both ways.
both ways?
Yeah.
Okay.
Okay, and then you begin from the very first A to check the neighborhood.
The last one,
Which
yes.
is- Okay.
Just as a periodic example, this is variety because it's kind of indistinguishable. It consists of the same substrings. This is actually the reason why there is no point on the diagonal.
And it's just
So-
checking the neighborhoods of the A characters only
For each character.
for each character.
If there are 2 characters, you have to run that algorithm for each character, basically.
So it's for each character pairs. right? It's like you have to compare two A's and every two B's, right? Something like that.
As an optimization, yes, that's right.
So it's not part of the definition, but that's an optimization if you compare it in pairs. Is that right?
Sorry?
Yeah, so the specific, like if you were to think as a programmer, right, you're trying to write the rules to determine the variety here. You take, for each character, you start from the left and you compare its neighbors. But when a neighbor is the same as the character you're comparing, you extend the radius, you extend how many steps you try to find the first character that is different to it. And that's part of the measure of difference. So if you're extending, the first time you're extending 5 places until you hit a B, then that's part of the definition. If in the second instance you see an A, you have to extend only 3 places, then that makes it different to the first A. Because the neighborhood is basically different. Right? Yeah.
Yes, the neighborhoods are different and the algorithm stops there.
Okay.
So
Yeah,
so
so
you can basically compute all the neighborhood of every character, and then you just compare whether they like isomorphic, have some isomorphic neighborhood or something. That's how you compute it.
Yes.
I don't
I
Is
think
the code
it's
simple or not?
complexity is
Maybe you just
at the
can
moment
show the
quite-
definition.
Sorry?
Do you have the definition? Like,
The definition of the function.
yeah, is it
I think
readable?
it's on my GitHub repo. You may check it there. It's in this function.
okay, and then if it's a if it's Leibnizian, does that mean it's just above 0 for the variety, or is there like a
Yes, because the variety is calculated as sum of 1 over absolute indifference values, and they are positive, so it's kind of positive. We just use the number 0 to distinguish non-Leibnizian ones for kind of ease of calculation.
right?
So for
Yeah.
yes, for Leibnizian it's positive. It's actually a rational number.
Interesting. So it's always rational.
Yes, because the absolute indifference is rational. It is the maximum of what we just calculated, the relative indifference values. So it's an integer, positive integer, if it's Leibnizian. So that's why it becomes a rational number. So shall I continue, or would you
Yes,
like to add
I'm comfortable enough for where now. Is there anyone else need to further understand? I think I've got a grasp of it. Great, thanks.
No. Okay. We just talked about the physical paths, but let me just kind of recap. We consider paths from the head node to the elements of the branch graph, which we regard as target strings. If a path contains a non-Leibnizian string, it is seen as non-physical. If there are no such non-Leibnizian strings in the path, they are physical. Okay, so this is the graph. BSD action is the sum of variety values of each string on a physical path. For example, when we calculate the first 10 paths, these are the BSD action values. So it is defined in this way. Action is needed because when we introduce the concept of path sums, that is similar to path integrals, action has a key role in calculating the amplitudes. So we have the list of physical paths, and we have their action encoded as the first element in a length 2 list. So among them, we calculate the maximal variety paths. These paths, in this case, there are only two. This has the highest value of action defined on the physical paths that we just mentioned. When we highlight the maximum variety paths, they are kind of a very small part of the multi-way system. I'm not sure if you could see, but there are some red paths.
And those are
Okay.
paths of the most action or the least action?
Yes, exactly. Yes.
The maximum action. And
Exactly.
action again was, can you repeat what?
It is defined as the sum of variety values of strings in a path.
Okay.
Okay, what we have at hand are strings, paths, and action. So in a way, we may need to find a kind of Hilbert space representation. For that, I was inspired by the cellular automata interpretation of quantum mechanics, which basically says that in the Hilbert space describing a quantum system, one basis is singled out as the ontological basis, and the time evolution of the system is represented by a state in the ontological basis hopping to another state. So this is the kind of the basic idea in this model in the cellular automata interpretation of quantum mechanics. Yeah, this is another way to put it. I chose the ontological base elements as the last nodes in the maximal variety paths. This is in line with the maximal variety interpretation of the Leibniz's theodicy, which means that we live in the best of in a world that has the most variety. In contrast to the original Leibnizian idea that we live in the best of all possible worlds. So this will be the basis of the Hilbert space that describes the quantum system that we just talked about, a quantum system of cyclic strings. Okay, we have paths, strings, and we need a way to assign vectors to strings. So an idea for that purpose would be to use the word-to-vec algorithm. But word-to-vec algorithm works with sentences and words. So by using physical paths, we converted each path to a sentence consisting of strings. These are kind of codes for that. For example, the first four sentences are like this: 2, 3, 4, 5, 6, 7. Yes, for depth 6. These are sentences. Then I did the word-to-vec. I trained the word-to-vec model and imported the vectors. So these are the vectors that correspond to the ontological base elements. They are kind of different. They are described by these two red arrows. And the other ones are the vectors corresponding to the other strings in the multi-way system that I found in physical paths. So a word-to-vec algorithm is basically a neural network. Okay. I mentioned the basic idea for assigning vectors to strings.
So you vectorize the strings
Once we
using
define the BFT,
a particular neural network.
From physical paths, we create sentences, then we train the model with the sentences that are obtained by the physical paths.
And this pod is showing what? Exactly.
This part is showing that we can assign vectors to abstract strings as found in the multi-way system. So it's a way to assign vectors, basically. There may be other algorithms which may be used, but I'm not sure of alternatives at the moment. So this is basically used to assign vectors to strings in order to interpret them as elements of Hilbert space.
Is it two-dimensional? How many parameters are we looking at here? For these vectors, it's two vector, right?
Yes, actually we enforce the dimension by choosing such ontological elements, but there may be more, let's say, general approach, such as using principal component analysis or similar approach.
Yeah, that'll be interesting for maybe a further study.
But what kind of corpus of strings are you training on then? Because usually Word2Vec is like trained on human written texts. What about this case then?
No, they are trained on the sentences created from the physical paths. For example, this one is one sentence that is given as an input. This is the second one. So they are not the, let's say, human words that we use.
There's no existing weights. It's just the Word2Vec algorithm that's used. It doesn't come with its it doesn't come with a model, with the trained model. Yeah.
It's from scratch.
So you train on multi-way, all the paths of the multi-way system as sentences. Only physical.
Part. Yes, exactly. Only the physical part.
And how many sentences in one training?
Let's see. Actually, we can calculate.
And it's just for the one set of rules, right?
Sorry for?
It's only for the one set of rules. It's not like there are multiple multi-way systems.
No. They're for single multi-way system. Yes.
And a single initial condition, no, right? All the sentences start the same.
Yes, they start.
Okay.
Okay, we were about to talk about path sums and S matrix. Once we define an action on paths, so we can do what's called path sum, similar to path integrals. And the summoned is this particular function. S is the BSD action, I is the imaginary unit, and we introduce a non-dimensionless coupling constant, K, just to control the, let's say, system. These are some complex amplitudes that are found using the idea that, for example, we consider all paths that begin with the same head node and the same target node. So we consider all of the paths that connected to, and we sum the value of this expression. And this is how the S matrix elements are kind of found. Actually, this is an S vector because we begin with a single head node. So just to kind of inform. And this is the plot of complex amplitudes. They are, I presume, non-normalized. And actually, this is an ongoing kind of research because what we have at hand are a definition for a Leibnizian strings, an abstract system of strings. And at the moment, it's not very clear how it's related to known physics, especially the condition of being a Leibnizian string. So this is an ongoing work. And what we have just provided is a kind of proof of concept work. It is written here, yes, it should be studied more, and the connections with the non-physical systems should be made clear in the future, I hope. We have obtained a system for the cyclic string ontology, but I think a similar work could be done for the hypergraph ontology of the Wolfram model. So that's it with the bird-say function.
That's great.
Hmm.
Yeah, so I had a quick question on the vector, the plot of the vectors there in 2 dimensions. My intuition would say that there would be some kind of like self-similarity or not self-similarity. There would be like a reflection
Mhm.
in the shape. So do you have any idea why there's not a reflection there? Is it part of the algorithm? Is it because it uses some kind of like randomization or every time you run it, it will be slightly different because of the algorithm?
You mean the word-work algorithm?
Yes, yes.
So actually, I couldn't understand your question because are you saying that one uses random numbers or?
Yeah, so I was just thinking like this is, oh wait, how many letters are we looking at? 3 letters, right? 3 characters. It's combinations of, it's words that have combinations of 3 different characters every time.
In this case, no, there's
Oh,
kind of
it's 4.
Mhm.
Okay.
Well, yeah, the D's only appear in the first root word.
Yes, the first word appears in all of the sentences.
And these sentences are the same up to the third.
We may check actually. 1, 2, 3. No, they may not be the same. Yes, because there are 1, 2, 3, 4, kind of 4 notes at the first step. We may consider a larger example. Let's say, for example, this one is different in this case. Yeah, they are not kind of the same for each sentence.
That's
So
interesting.
are my eyes deceiving me? Is the first 2 sentences identical or there's something different?
The first word.
Oh no, there I can see the difference. The second last word has got a difference in the characters.
Yes, there's
Of the first 2 sentences. Okay, so every sentence there has at least some character difference somewhere. Yeah. Okay.
It may be also the case that, for example, there may be more than one application of a rule that connects the two strings. So in this case, it's doubly counted.
Okay.
That may be one aspect of it.
Yeah. And then what is the connection to quantum? I might have missed that.
The connection first, we need vectors to represent strings if we are to interpret them as elements of some Hilbert space. So this is
Hilbert
one
space.
aspect.
Mm.
And the second aspect is to try to find a kind of probability amplitude to get head node from target node from the head node.
I mean, how are the negative probabilities forming here? Or are you
This
doing it without
also the
negative probabilities?
amplitude. So the modulus square is positive.
Okay.
I think the question here is like, how do you justify like the whole path integral approach? Why would you need to sum up all the vectors there, right? So you encoded all the words as vectors, and you have a path of those, and you sum them up. That's basically
No,
your.
actually, this is different. This is just the sum of this expression over the paths that connect the head node to some particular target string. And these are kind of probably independent calculations. So these are not the sum of vectors that we see in this plot. This is sum of e to the I action divided by k. I'm
And
not
actually,
sure.
there's variety.
So did you?
What-
Okay.
What's the action? The variety? Which string? What?
Yes, some variety values, yes. Actually, we have an example here. For example, for this path, we have the action value 70. For that one, 69, and for that one, 71. So for a specific head node and a target node, we consider all the paths that connect them, and we sum of e to the I s divided by k, where s is this number. This is the sum of variety values. It's just a definition.
So do you have any idea how to interpret the amplitude then?
In the simplest case, it may just represent a kind of transition amplitude, but in order to give an interpretation, maybe first we need to find a more, let's say, concrete realization of this abstract system. So these are my ideas at the moment.
Is there anything like destructive interference?
Because you
Among the
sum the,
paths, that
you still sum the amplitude, so it is there. It's just not clear what the amplitudes represent. It just seems like pretty ad hoc.
yes,
You just interpret variety as your action, as a complex phase.
Mhm.
Right.
Interesting. And then an earlier question that Nick had was, what is the intuition about why it's called physicalization? Like what makes it more physical if it's more variety? Do you have a comment on that?
Actually, the degree of variety, it doesn't make one string more physical or less physical. It's the idea that if there are at least one pair of characters that share the same neighborhood structure, then this is the kind of condition for physicality. So they cannot represent monads, and since we consider a monadic interpretation, we need to regard them as non-physical. So that's basically.
Oh, wait, maybe so did I have it in reverse the entire time? So when you're saying when there is a duplication of neighborhood structures, that's what increases. That's what makes it physical. Not that it's unique. Like, not that every neighborhood structure has to be different. Maybe
Actually, what you're saying is correct. Yes, the last one is. Maybe we
okay.
can go on to the examples.
I guess you need to be fluent in philosophy of
Leibnizian philosophy.
Leibniz monad.
Actually, I have a kind of summary of the whole idea in my Foundations of Physics paper. You may check that if you, in your free time.
Yeah, that would be great if you can actually link all those things afterwards. If you can share the link, we'll put it in the description of the video that will be on YouTube, this video.
Sure.
So people can refer to the paper and the GitHub as well. Yeah, it'll be very interesting. Yeah, so I was just thinking like maybe it's to do the physicalization concept is to do with like because there is ambiguity associated with the structure in terms of neighborhoods that are the same in multiple places. That's what gives it more of like quantum effect, something like that. So if it's a monad, it's kind of like not quantum by definition, because it's like identified. It's like there's an observed reality, like in a physical instantiation of it. But where it itself could be where the characters could have like ambiguity as to its position, that's what makes it like more quantum. Something that's the intuition I'm kind of like latching onto there. Like the
Actually, I
degree
was
of ambiguity.
thinking about the reverse direction because, for example, when we consider such a string, let's say ABC, but reversed,
Mm-hmm.
the A,
Yeah.
it has zero variety. I kind of like to interpret this as a fermionic system, maybe. Or yes, so
Because it goes in both directions.
yes,
Like you have,
Mhm.
yeah, you have to check the neighbors in both directions. So you're traveling forwards and backwards in time in the same, like you're looking forwards and you're looking backwards.
Yes, actually, it's a trivial. But
You're looking in both time directions, so to speak.
yeah, yes, in some sense, yes.
Something like that, yeah. It's very cool. It's all new ideas here, so that's why we're trying to like figure it out step by step. But I think this is really cool, and what I like about it is you're working with very simple things, very simple constructions that you can build up quite nicely, and it lends itself very nicely to doing enumeration and computational experiments with the structure. You know, like you can just throw it into a Word2Vec, which is pretty cool. That's a great idea. So this is a nice area. I appreciate you explaining this to us. Cool. Any questions in chat, Dugan?
No.
Oh, no questions. Oh, okay.
Just a last note, maybe.
Yeah.
What we have.
Well, actually, I mean, there's
Well,
one question. Did you write quantum phenomenon in shape dynamics?
Yes.
Okay. And they go on to ask, were you suspended from entering Italy for some reason?
Let's say maybe later I may talk about it.
Okay. Well.
Any other questions from anyone in here? Okay, I think we're good. Cool. Yeah, appreciate the chat. And then yeah, please do share the links with us, and we'll have them in the description.
Thank you so much.
Thanks, everyone.
Thank you.
Do